Thank you very much for having me. The title says what it suggests. So in this talk, I'm going to present the Benthem characterization theorem for ultrafilter extensions. But before starting, I just want to get into the middle and read the theorem, and then in the first steps slowly digest what the content is. This theorem was proved in Benthem's dissertation at 1976, although this formulation is not the original version, but this formulation became the well-known and the popular one. And since then, a lot of other model systems like mu calculus, hybrid logics, intuitionistic logics came up with their own characterizations that try to somehow imitate the classical one. And this theorem has this motto phrase according to which one can hear this expression that model logic is nothing but the dissimilar invariant fragment of first order logic. And to see this, let us check, or let us understand what are these notions that the theorem says. Namely, a first order formula with one free variable is equivalent to a standard translation of a model formula if and only if that formula, this first order formula, is invariant for bisimulation. So this is a theorem connecting a syntactic condition to a semantic one. And for this, basic model formulas are nothing but simple extensions of basic propositional logics with these operators. But for the next, next part of the talk, we will forget about what model formulas are in these settings. But whenever I'm talking about model formulas, I will understand first order formulas in some translation ways. Namely, the standard translation gives us the input is a model formula from this language to a first order language which has a single binary relation symbol, and for each propositional variable we extend the language with a unique unary predicate symbol. And the translation is very intuitive and does the following: that every propositional parameter is translated to this atomic formula. If you have this conjunction, this is done in the usual way. Negation is handled in the usual way. The only non-trivial difference is what do you do with this diamond symbol, and diamond symbol encodes somehow in the Kripke semantics the accessibility relation. That's why we say, or we just give back this intuition that diamond phi is nothing but, from now we have to think of it as a first order formula which expresses this property. And the top is, let's say, this is something like validity. An important fact or an observation, good to know, that each standard translation gives us a formula with one free variable. So just in short, whenever I'm considering a basic model formula, it's good to think about actually the standard translation of that formula, so that we don't have to bother with these model logic expressions and so on and so forth. Everything will be just standard from first order logic. So we have done with this model formula part and the standard translation part. And what bisimulation does is the following: that given two models of that language, of this first order language, such that we pick such that we pick W from M and B from N, and the binary relation between M cross N is a bisimulation. If the following zigzag condition is satisfied, the intuitive idea is very much the same from Ehrenfreud-Felscher games, but this is somehow handled in a local manner. Namely, that whenever W is Z related to W prime, such that W is related to a guy V, then, and this happens, for example, in model M, then this situation will be somehow modeled or imitated in the model N. So we will be able to find a pair V such that they are related, and according to the relation R, but also they are related according to this bisimulation relation. And this is usually called the fourth condition, and of course we have the back condition. And the next step, I will introduce these notations that this two Bayes arrow will indicate the fact that between model M and point W and model N and point V, there is a bisimulation. And as a matter of fact, let me express or emphasize that whenever we find a bisimulation between two models and the corresponding elements, then by this notation, I will denote the fact that the model formulas are the structures satisfy the same model formulas when you implement in place of the free variable x w or in place of the free variable x v, because as I mentioned, first order model formulas are nothing but some type of first order formulas having exactly one free variables. So the message here that bisimulation implies is model equivalence. And finally, the notion is, what does it mean that something is a formula is invariant for bisimulation? Has the following content. Whenever we have two models, M and N, and we pick W from M and V from N, then if there is a bisimulation between these structures, then that formula is true if and only in one structure, if and only if it's true on the other structure. So having these notions, that let me just recapture again the content of the theorem, that the first order formula with that free variable x is equivalent to a standard translation of a model formula if and only if this first order formula is invariant for bisimulation. And from the perspective of modal logics, there are many classes that are quite interesting and very hard to overestimate their importance. For example, the class of finite models, because they are the key for decidability, because modal logic has the finite model property. The other very important class is the descriptive models. They are models for this language with some stone space, such that the interpretation of the predicates are usually can be only the elements from that topology, but the importance of this gives rise to general completeness and algebraic and topological duality. And the last one, which will be our key point in this talk, is the class of ultrafilter extensions, which are nothing but analogs for ultraproducts and such structures, which are in first order logic, but these constructions here live in modal logic. So what do we know from this construction is the following, that if we fix a class of models K, we can relativize this notion that what is invariant under bisimulation in the following sense, that we can say that the first order formula with one free variable is invariant for K, if and only if it is invariant with respect to K, with respect to all elements of K's, all models from K. And what it is recently have been shown that we have the following equivalences, which are the restrictions to these very important classes that I have just mentioned, that namely first order formula alpha x is equivalent to a standard translation of some model formula, just in case if it's equivalent invariant under bisimulation with respect to these descriptive models. This is proved in this 2022 by Bezanishvili and Henke, and the third one is that alpha is invariant for bisimulation with respect to finite models. This was proved in 1997 by Rosen. And of course, today the aim will be to add the fourth here to prove it with respect to the class of ultrafilter extensions. But let us check or see what ultrafilter extensions are. For this, let me introduce the notation that basically for a relation, for a subset of our model, this diamond Rx will be nothing but the set of R predecessors of X. And having this notion that if we start with the model for that language, for this appropriate language, its ultrafilter extension is the following structure, where the underlying set is the set of all ultrafilters over M. Two ultrafilters are related if and only if whenever I pick a big set from V, this R diamond X will be a big set in U. And this is for the relation, and for the predicates, These are quite standard interpretation of a predicate with those ultrafilters for which the interpretation of P is already belong to U. And some notation that pi of W will be the principal ultrafilter generated by W, and this MUE will be the class of all ultrafilters for this language. And there are some facts, and before the facts, let me mention this very important definition, the M saturation, which is akin to the standard saturation for first order logic, namely that the model M is M saturated if for all set of model formulas and an element from that model, if gamma can be finitely satisfied in some successor of W, then I will be able to find the successor of W in which the whole set gamma is satisfied. And as a matter of fact, similar to Bosch lemma, here in the model case, we have that an ultrafilter extension is always modally equivalent to the original structure. And as for the saturation part, the implication for model equivalence and bisimulation, actually they coincide because now model equivalence implies bisimulation. So these are for the facts. And as it turns out that for the case of finite structures and descriptive structures, there are no completeness theorem. Why this is important? Because the original proof for van Benthem used not completed compactness theorem. The original proof from van Benthem used compactness theorem. And as a matter of fact, it turns out that that very same strategy from the original proof cannot work, because here we also don't have a compactness property. The claim is that the class of ultrafilter extension is not compact over first order logic. Here is a very simple argument to see this, that we pick this set of formulas which basically says that we talk about linear ordering, and this says that, okay, for each n we extend successively the ordering, and it is easy to check that every finite subset of gamma can be satisfied in M. Why? Because every, take the initial segment of the natural numbers, this structure is isomorphic to the ultrafilter extension, so definitely this structure will be in this class. That's why it is satisfied. But there is no ultrafilter extension that can satisfy the whole gamma, and basically the idea is that since every structure is embeddable into its ultrafilter extension, already because of these formulas, saying that it's a linear ordering, these are universal formulas, so they are also have to be true in the original model. As a consequence of this, there should be an infinite chain already existing in the original structure, and any ultrafilter containing this infinite chain will be reflexive, which contradicts the structure being irreflexive. So let me introduce some further concepts that we will use during the main proof to prove it for ultrafilter extensions. And if given a structure M, the unraveling cover of M will be denoted like this. And this is nothing but the set of, this is a forest which containing the set of all paths consisting of this relation. So the underlying, the universe consists of the set of all finite paths, and two finite paths are related just in case when one is the extension of the other. And that what is the interpretation now of the unary predicates is nothing but basically just the projection to the last coordinate, and I check it whether it is in P or not in P. And as for the next one, as a matter of fact, the unraveling cover is bisimilar to its original structure. So having this unraveling cover or unraveling tree, sometimes this is the notion, we define the next one, which is nothing but the concept of multiplier, which goes as follows, that given a structure for that language and we fix a cardinal kappa, the kappa multiplier of the structure is denoted by this, where the universe is M cross kappa. The relation is defined in such a way that two guys are related if and only if it's already enough to have related in the original structures, and other coordinates are quite a lazy coordinate, because for all arbitrary choices, you can put your favorite cardinal, and it will be already related. And as for the unary predicates, the extension will be nothing but the extension of P cos kappa. And again, as a matter of fact, the projection to the first coordinate is a bisimulation. So the kappa multiplier of M and M are bisimilar. And another lemma that we will use, that if given two models such that they are bisimilar, and it's enough to have one to be M saturated, then the other will be M saturated as well. And here is the key lemma, and this is the part where I'm basically cheating, because this is the hard job is done by Bezanishvili and Henke, but it turns out this will be very much suitable for our case, and which intuitively says the following: that if given two structures have this have of this form, so they are glued together they have some common part X, but they glued together with A's and B's, such that each AI, AJ are isomorphic, and also BI and BJs are isomorphic. Moreover, these index sets are infinite, and we'll let L to be this 3 to the n. Usually this will having to know something with the Ehrenfeld fresh regime that we will use. So this is a parameter. Then we have to moreover suppose that for each AI there is some, so for each W in AI there is some BJ such that the neighborhoods are isomorphic, and here the notation is that the L neighborhoods are isomorphic. It is nothing but you imagine the structure which is generated by W in L steps according to the relation R, and this is nothing but the substructure given by R in L successive steps that you can reach. So if these neighborhoods are, and then we suppose that these neighborhoods are isomorphic, then what we can show that for any element, W0 and V0 and if the neighborhoods, corresponding neighborhoods are isomorphic, then they are equivalent in up to, they are first order equivalent up to quantifier depth n. And this is like Ehrenfeld Fresher type proof that they are using, but this is really one of our key lemma. So basically we are ready to see and to prove the theorem for today, which has the following content: that given a first order formula, then the following are equivalent. That A is equivalent to the standard translation of some model formula phi, or this is equivalent to the statement that A is invariant for bisimulation with respect to the class of all ultrafilter extensions. And how we will prove? We will make a twist and turn around with this construction of unraveling covers and multipliers, and using bisimulation and the lemma that we have done so far. But 1 to 2 is trivial. It holds for every bisimulation. Always in general proves that 2 to 1 is the hard part. And let us fix a bisimulation invariant formula, which is bisimulation invariant with respect to the class of ultrafilter extension, and set this lambda L to be that parameter. And also assume that M and N have these respective universes, such that V0 is M, and W0 is in M, and V0 is in N. And we assume, moreover, that M satisfies this alpha formula in plugging W0, such that they are bisimilar up to model depths L. This is the notion that I didn't want to overburden the notation and the definition, but this is something very similar that quantifier depth N, but here we talk about model depth N. And the strategy is that we will show that it is enough to prove that alpha is invariant under L bisimulations. So our assumption is that it is invariant under bisimulations, but this is invariant under this model depth bisimulations, which has the very intuitive meaning that if this is true, like M satisfies alpha and they are invariant under this L bisimulation, it happens if and only if that then M has to satisfy A V0. And for that, we set the parameters that kappa be the maximum between the coordinate M and N. And just for technical reasons, that in order to save spaces, denote this pair like this W0 hat and V0 hat, which are coming from the kappa multiplier. And this is easy to see. If they were lambda L dissimilar, then the kappa multipliers will be also a lambda dissimilar. And now we are trying to argue in the general way. So here we can see the kappa, the ultrafilter extension of the unraveling cover of the kappa multiplier, which can be in general written as a disjoint union of some generated substructures. I'm not getting into the details, but all the messages here that that structure can be decomposed into some simple ones and glued together, and it will be exactly this structure. And this is the same for the other structure, which starts or originates from N. And here, what we can have in the next step, that if I glue together these two structures, it will be isomorphic to first gluing together, then taking the ultrafilter unions. So here I just make the ultrafilter extension, then gluing together. Here I just reverse the order, which turns out to be isomorphic to a structure which has these components, like these gluing together, and some other components X and Y. So why this is good? First of all, we see that this structure is already in MUE, the ultrafilter extensions, class of ultrafilter extensions. That's why it will be important. And this is very similar to the conditions that that was given in the key lemma. So in the next part, actually, I'm not getting into the details, but one can also calculate what these X and Y are. These are some decompositions of some ultrafilter unions that I'm not even going into that point. But the main point here, what I have mentioned, that now this structure belongs to M. And then we can observe that for each cardinal lambda eta less than kappa, these parameters does not matter. So here is eta and here is lambda. They will be isomorphic because of the structure of this kappa multiplier and tree unraveling. And from this isomorphism, because of this isomorphism, it follows that also then if I just lift up to the ultrafilter extensions, they will be also isomorphic to each other. And moreover, we have a chain of bisimulations, namely the original structure by the facts is bisimilar to the multiplier, which is by the facts bisimilar to the unraveling cover. And in general, the structure and the ultrafilter extensions are modally equivalent, but as they are both M-saturated by this lemma, it follows that they are bisimilar. And since by assumption A is preserved under bisimulation, we have that this structure satisfies this. Okay, that this structure, at the end of the day, it satisfies this formula because we assume that this structure satisfies A, and composition of bisimulations is a bisimulation, so we end up having this structure satisfying alpha. On the other hand, we can keep continuing this track by using the properties tree, because bisimulation is invariant or blind to gluing together structures. So that's why if we have already this guy here, it will be bisimilar. If I just glue together the structure from which I started the end part, and by the observation, this is nothing but first gluing together, then making the ultrafilter extensions. And then since alpha is again invariant under bisimulation, and of course every isomorphism is a type of bisimulation, I will have that this big structure satisfies alpha, the formula alpha. And furthermore, the lines we have here, we can also repeat it for the structure where we start from N, not from M. So this is the only difference here. And now, as I mentioned, these the decompositions of the original structures just satisfies the conditions of this key lemma. So we can in plugging these parameters, basically we can use that key lemma here, and it says that the conditions are satisfied. It is only left to show that actually these Geifmann neighborhoods or these neighborhoods are actually isomorphic, but we are lucky in this position because to prove it, actually we can just repeat the proof from the Bezanishvili and Henke, and therefore we can conclude that these structures are Q alpha elementary equivalent. Consequently, this structure satisfies this guy, and we are almost there because if following this line of equivalences and this one, we end up that n satisfies alpha, which was our goal. So alpha is preserved under LB simulations, and now the very last lines that this is a general fact from, I don't know, finite model logic, that LB simulations are equivalent to L model equivalence, and hence this formula is characterized by some collection of theories of formulas of model depths at most L. But this is also a fact that there are finitely many such formulas. So there is a model formula of depth at most L, which is equivalent to alpha x. And this is the end of that story. Thank you very much.